Welcome to another open learning session where I'm going to catch up with deep learning. So we are doing the SMAth textbook. The last chapter was about inverse matrices, and now we are reaching chapter 2.2.3, multiplication by a scalar. Let us look at what happens to matrices when they are multiplied by a scalar lambda from the real set. Let A be a matrix m times n and lambda an element of the real set. Then when you scale the matrix A with lambda, we call it K. And K is equal to, you scale each element with the same factor, the same scalar. Practically, lambda scales each element of A. For lambda and C, element of the real set, the following holds. So I had to look this up. C. Okay, so lambda and C is, they are both just numbers. And what they said is if you scale the matrix, it's the same as if you scale each element of the matrix, the same factor. So pretty much similar to when you scale a vector. Okay, so there are a few properties here. So the first one, associativity. Lambda times C, matrix C, is equal to if you do first C times matrix C times lambda. So the order does not very much matter because both are scalars basically. So you have two scalars, lambda and C. And what they're saying is if you do like first one and then the other or other way around, it's the same thing. So this also includes abstracting out the scalar. Just the order in which you're doing the matrix multiplication is important because the order has to be the same. So let's remember, B times C is not always equal to C times B. Like it can be in case it's an inverse, but in case it's not, which is most of the times, then the order is important. So, but this is just for us to remember. What they're actually saying here is that you can abstract out the scalar. Also, you can put the scalar in the end. These two are the same things, like because it's equal. But in the first case, you had the scalar in the beginning, and then you had it at the end. Okay, yeah, that's what they also say. This allows us to move scalar values around. So what is this third one? Okay, so the third one says that because a scalar is just a number, if you transpose a scalar, it's still the same thing, right? There's nothing to flip. So if you do the transpose, it does not really matter where the scalar is. It can be like before you do the transpose operation, it can be after, and you put it in the end. You just transpose a matrix and then you multiply with the not transposed scalar. You do the not transposed scalar and multiply it with the transposed matrix. So it does not matter. So if it does not matter, then I just will remove that. Okay, so the next one is distributivity. And I think like the big difference between those two are here you have a plus and here you only have a multiplication. This is my naive view. Let's check what was how was the other rule here. We also have those two. And here again, you have the plus here. and the associativity only had the multiplication. So what it says is you can factor out basically the plus and then do the addition first and then the multiplication. So when you have something like that and you multiply it with the same matrix C, you can just do the addition with the scalars first, and then you have to do only one time the multiplication with the matrix. Yeah, and it's also true for the matrix. So you can not only factor out the scalar, but you can also do it for the matrix. So you can just add those two matrices first and then multiply it. You don't need to multiply each one and then add those sums together, those matrices together. Okay, so here's an example. I will just not look at the rules. Let's try to do it in our head. If we define C is this, it's a 2 by 2 matrix, then you have two scalars, lambda and psi. So what are they doing? They say lambda plus c, so do the multiplication, do the addition first and then multiply it with c. I think we can do it element wise. Yeah, so we have still a matrix C, and then what they do is they just add, just multiply the sum of those two scalars here. Then they do the calculation. Exactly. This is the calculation here on the right, here. And basically what you have is when you do matrix addition, you have still like those two matrices on top of each other. And you punch the holes, basically, right? This is how I imagine it. So let's say you have two colors for these two matrices. You have blue and you have yellow. Then basically what they're saying is the first term is yellow, which is exactly this one. And the second one is blue, which is this one. And that's how they prove that this is blue and this is yellow, and that is the same thing as, that's the same thing as this one. Yeah, that makes sense. Okay, so let's go to the next point. 2.2.4 compact representations of systems of linear equations. Okay, so now it's about how do we write it while being lazy, right? That's what compact always means, being lazy. And lazy means dense. Well, if you want to be correct, like you don't skip things. That means that you have to put like more information into less symbols, which also means that reading it is harder. If we consider a system of linear equations. Okay, so this is again our system of linear equations. And it's not just three equations where they have like some symbols, sharing some symbols, because these are actually expressing the same thing. This is why it's called a system. And use the rules of matrix multiplication, we can write this equation system in a more compact form as, yes, that's what I think we all learned in high school. What they're doing is they're taking the coefficients, basically, they put it here, then they abstract out the vector. This is basically a vector. And then you have the solutions, basically. It's not the solution, but what is it? The value, let's say value on the right side. Okay, so we have to understand that this is the same thing as like the other one. It's just a different way to write it. And what they're also not writing here is the plus sign, and also So this is a multiplication here. And because we are doing the matrix multiplication, we are doing like this, right? Each line goes and like on the right side, each x line, each vector goes on top of the coefficients, which will form exactly one of those equations. Note that x1 scales the first column, x2 the second one, x3 the third one. These are basically all, yeah, they scale because you do x1 times 2, x2 times 3, x3 times 5. So that's why they say they scale. Generally, a system of linear equations can be compactly represented in their matrix form as ax equals b. Okay, so this whole thing, when mathematicians are writing ax equals b, then what they mean is this green thing. And this green thing actually means a system of linear equations. This is like compressing, right? That's some kind of hardcore compression. Okay, let's continue. And the product AX is a linear combination of the columns of A. We will discuss linear combinations in more detail. I guess this chapter I will not put any notes in. I already know that is how this works. Okay, I think I will make a short break here, and then we will see each other in the next video.